Okay, wonderful. We are recording. We're recording the meeting. And let's begin announcement number one. Concerning our midterm, which is on Friday, midterm number 2, I have posted a more detailed information sheet. Furthermore, there is a sample exam, as you know, and I placed a file. In other words, I added a file to that folder. Okay. This was based on some discussions we had during office hours, so I thought it'd be useful to share those discussions with everyone. we drew some diagrams, etc. Okay, furthermore, homework 8, I did also add a file there. It's a nice picture from some tremendous time in the space program, the Apollo missions, and it helps to clarify what's going on in problem number 3. So those are the announcements. Let's return to our discussion. We are now very much in chapter 11. Okay, let's talk about what we're doing. We have a problem here, a very nice concrete problem. This particular piece of paper is from our last lecture, all right? And what we're doing is we're analyzing the motion of these two objects. We're going to treat them as point particles. Certainly, we're ignoring the little railroad wheels down here. Let's ignore the moment of inertia. My goodness, that would be a really one more headache we don't need right now, right? So we're going to treat these two things as point masses. So we have a mass M1, a mass M2. It is a case of a one-dimensional space. We have an x-axis going to the right, and we have these 3 springs. So we set up the problem last time. It's useful to measure x1, the position of this object, relative to its equilibrium position. Okay. Having said that, we have incorporated various things we know to be true about springs. Springs are known to have rest lengths, the so-called unstretched length of a spring. Okay. So having said that, what can we say about this apparatus? We would need to know the length, the distance from this wall over to this wall. We'd need to know the lengths of the individual railroad cars. We would need to know the rest lengths of these springs, okay, to write out a detailed formula to compute the extension of each spring relative to the rest length. So we could do that, but it's much more expedient to observe that whatever the rest lengths may be, and whatever the distance from this wall to this wall may be, and whatever the lengths of the individual railroad cars may be, there must be some sort of equilibrium position. Okay, and let's just, for concreteness, assume all the springs are under a little bit of tension. Okay, just for concreteness. So relative to this equilibrium position, we're going to use a symbol x1 for the excursion away from that equilibrium position for car number 1. Okay. And if you move a distance x1 to the right, then the force provided by this spring has increased by k1 x1. So in that sense, we do not have to worry about the equilibrium lengths of the springs, et cetera, and so forth. We've distilled the problem down to these observations. The total force on car number 1, we must have a minus sign because k1 is pulling to the left, k1 x1, like so, and then a plus sign here. This spring is pulling on this car to the right. We have the plus sign like so. So it's possible to go through these equations and write out the forces. The result is we arrive at these 2 wonderful equations. We have a case of coupled differential equations, right? This has been a theme in our course. And as you know, for an exam question, having 2 coupled equations would be reasonable. Having 3, not reasonable for an exam. We can do that on a homework problem, but for exam problems, 2 coupled equations is our limit. We do have 2 coupled equations here. Notice that the left-hand side has a very special structure. We have mass 1 times the x1 double dot. And looking ahead to this preferred formulation, right? In this formulation here, we've assembled these 2 coordinates. These are examples of generalized coordinates. We've assembled them into a vector. So we have this two-component vector. It's simply a collection of these two functions. It's understood that this is a function of time. We could write x vector as a function of t. And here you would have x1 as a function of t, x2 as a function of t. Right? It's understood that these are dynamical variables and they're functions of time. So the left-hand side, notice it has the structure of a diagonal matrix times times r, and let's fill that in here on today's piece of paper. Okay. The structure that emerges here is shown in this very dramatic box. What we're seeing here is we have a mass matrix times an acceleration vector equaling a k matrix. Did I get the sign right? I'm a little concerned about a minus sign here. This is very important to us. Okay, wait a second. Yeah, there's a minus sign here. Sorry, folks. This has got to have a minus sign. There. Much better. You see, this is very much a two-dimensional version of a familiar result from Chapter 5. In Chapter 5, we were very interested in the simple harmonic oscillator. And there, you essentially have the one-dimensional version of this equation, mass as a scalar times the position double dot, equaling minus a constant, a spring constant, times the position vector. This is now a two-dimensional version. And here we have to be very careful about these matrices. Let's talk about the matrices. You can read off the matrices from this collection of two differential equations. Okay, so as I was saying, this is, okay, so for this problem, the mass matrix is diagonal, and we have exhibited the two diagonal elements here. It's, for extra clarity, we can write the zeros. This is what it means to be a diagonal matrix. The diagonal is populated by the eigenvalues, right? In this case, the eigenvalues are M1 and M2, and the off-diagonal elements are 0. So there you go. We have the mass matrix. Now the K matrix, let's emphasize, this is a 2 by 2 matrix. And so you can see I've inserted liberal amounts of space here. I inserted a huge space. When we write out matrices, we do not put commas to separate the elements. We simply have open space. Space, the final frontier, is between these elements. So we're looking at a big space here, and then K2 plus K3. Okay, so these equations summarize the status of the problem for us here. And I've positioned the paper so we do have a view, right? So these musings here, this is something you would actually work out in your first year physics course, the total force on this cart, et cetera, and so forth. Now we've written down Newton's second law for both of these point masses. We're treating them as point masses. Kind of the new idea here is to formulate this with matrix multiplication. So having assembled the two dynamical variables, these are generalized coordinates, x1 and x2. It happens that they are Cartesian coordinates relative to equilibrium positions. But they're an example of something we talked about last time. We can call this Q1 and Q2, right? And lowercase n is the number of generalized coordinates. Okay, so having said that, you can verify that if you take this diagonal matrix M and you multiply by the x vector double dot, and of course the x vector double dot is x1 double dot upstairs and x2 double dot downstairs, two component vector. You indeed recover the left-hand side here, you get these two. This matrix equation is ultimately, after you multiply matrix times vector, the left-hand side is a two-component vector, and the right-hand side is a two-component vector. And that's precisely what we have here, this structure is visible in this box. Okay, so again, it's necessary to go through all the steps. This K matrix does have the off-diagonal elements, and you can see a very nice connection with our physical intuition. Notice the value of K2. Here's a K2, and here's a K2. We remarked last time, the reason these two differential equations are coupled is because of the non-zero value of K2. If you remove K2, that's equivalent to simply setting the value of K2 in these equations to 0. Removing it means there's no force, so that can be accomplished by just setting K2 equal to 0. And then you see the two differential equations decouple. That means the first equation involves only the variable x1, and the second equation involves only the variable x2. So it's very much this K2 spring that we're interested in. We're interested in the fact that you have these two coupled oscillators, right? If you remove K2, you have an oscillator here on the left, mass number 1, spring constant number 1. This would simply oscillate at its own natural frequency. And over here, mass 2, and this spring constant, we had to call it K3. This would oscillate. It would have its own characteristic frequency. Okay, so we're going to be looking at this coupling. We'll be looking at this from several different perspectives. Okay, but the first order of business was to recognize the structure and to appreciate that we can simply rewrite. This was just a transcription of the original differential equations into this form here. Now, in our last meeting, we also talked about other avenues for approaching these problems where the K matrix, here we have this K matrix, which emerged as a result of our analysis of forces. We're going to see that this K matrix can also result from a second order higher dimensional Taylor series expansion of the potential energy. So we're going to investigate that. So what we want to do here is start to bring in some of the theorems. We have some interesting theorems that are relevant to the discussion. These theorems are available in appendices in our textbook. And let's take some time to talk about these theorems. So it's useful to have this nice problem very clearly stated here. It's very helpful to have a concrete problem to think about. As we go through these theorems, the theorems can be rather abstract and technical. Okay, so with that in mind, let's have a quick look at these theorems. All right. Okay, so here's our textbook. This appendix is A1, diagonalizing a single matrix. Okay, we're very familiar with this because we've been studying chapter 10. We have the inertia tensor, it's a symmetric matrix, and it can be diagonalized by a rotation. Okay, we've been doing quite a bit of that, finding the principal axes. This is the real shocker, this next appendix. This should be quite alarming to anyone who studied quantum mechanics. This is blasphemy, right? Simultaneous diagonalization of two matrices. Okay, so let's talk about this. In quantum mechanics, if there's one thing they tell you, it's that you cannot simultaneously diagonalize two matrices in general, because in general, they do not commute. So there appears to be a very disturbing contradiction here. And we must resolve this. And when we do, we will emerge stronger than before. We'll have a better understanding. So the key to this resolution is what we talked about last time. Remember, a matrix is a rectangular array of numbers. Sometimes it's square. But it's used to represent a mathematical object. And sometimes we use matrices to represent linear operators. Sometimes we use them to represent quadratic forms. Okay, and so therein lies the distinction. So in quantum mechanics, obviously you're talking about operators, you're talking about Hilbert spaces. All right, and it's certainly true if you have two operators that do not commute. Okay, we'll go through an example, two matrices that do not commute. Then you cannot simultaneously diagonalize them For one thing, if you did simultaneously diagonalize them, they would commute. Okay, so that's a contradiction. When we speak of diagonalization, we're talking about changing basis. You have the same operator, the same mathematical entity, but if you change basis, then the rectangular array of numbers changes its appearance, right? The individual entries in the matrix will change, right, due to a change in basis. Okay, so in summary, in quantum mechanics, it's certainly true that if you have two operators that do not commute, then you cannot simultaneously diagonalize them, okay? The situation is different here. In chapter 11, we're very interested in quadratic forms. And we have two examples here. These are called quadratic forms because it's very similar to a quadratic polynomial. You know, in algebra, if you have a quadratic polynomial, you've got your variable raised to the second power. There could be some other powers in there, a linear power, a constant coefficient, but it's really that second order term that earns the name quadratic polynomial. So here, the notion is that of a quadratic form. This is a scalar valued function, the potential energy, and you see you have a homogeneous second order polynomial here. There's a K matrix there, right? We'll talk about how you can get this matrix from the second derivatives of U, but the point is you have some sort of matrix here, and sandwiched around the matrix as per this diagrammatic view, we have a construction. On the right, we have a column vector. On the left, we have a row vector. When you evaluate this product, think of this as a rectangular matrix times a square matrix times a rectangular matrix. You get a 1-by-1 matrix. So in this sense, we have a quadratic form. It's because we have second order terms. There's always going to, suppose Q is measured in meters, then you always have square meters here and all these various terms that could occur. Okay, and here's, you've got meters per second, meters per second. That's one possibility if you've chosen the generalized coordinates to have dimensions of meters. Of course, sometimes we choose our generalized coordinates to be angles or other convenient things. Okay, and so in summary, the contents of that appendix we just looked at, Appendix A2, the simultaneous diagonalization, what does that mean? If you have two of these matrices, for example, a K matrix and an M matrix, then you can find a new basis. You can change the basis so that both of these matrices are diagonal. Okay? And notice in this picture, we never multiply the K matrix times the M matrix, right? They occur separately in two different terms, but we never multiply them. In the world of operators, you certainly can multiply operators. You have a vector, for example, here's this omega vector. The operator gives you a new vector, in this case, the L vector. So it's a mapping from a vector space to a vector space. And that's the context you have in quantum mechanics. You have your Hilbert spaces, right? These vector spaces. Could be a two-dimensional Hilbert space for a spin 1/2 particle. But the point is, you can multiply another operator again. So in that sense, you often have products of matrices. And that's when we start speaking about the commutativity of the operators. What we're going to see here is with these two matrices, it's possible to be very dramatic with your change of basis. In fact, you can force one of the matrices to be the identity matrix. It's diagonal. And then clearly you can diagonalize the other matrix with a change of basis, for example, a rotation matrix. So let's go through that in detail. We'll work through a fun example here to see how this works. Okay, so here's a fun example. Okay, this is an example having to do this with the subject of the simultaneous diagonalization. All right, so let's consider, we're going to look at two matrices, and it's sufficient to have 2x2 matrices. In the world of 2x2 matrices, you can exhibit all of these fundamental things, the lack of commutativity. Let's write down these matrices. So we're going to define two matrices as follows. Okay, there's our first one. I guess I drew it rather cramped, but it's understood that this is a 2 by 2 matrix. You have 4 distinct numbers. It's awfully close there downstairs. There's a 0 on the left, there's a -1 on the right. Yeah, it's kind of scary how close. I should have put more space, okay? Here's the B matrix. Okay, and if you have had quantum mechanics, which is not required, you will recognize these as 2 of the Pauli spin matrices. So when you study a spin 1/2 particle, you're often looking at these, and there's obviously a third matrix, which we could write down. But for our discussion, this will serve to illustrate some important things. So first of all, observe, these matrices do not commute. Okay, what does that mean? If you multiply like so, if you compute A times B, and we're talking about standard matrix multiplication, here's what you get. On the other hand, suppose you multiply B times A. What happens? Again, a moment's thought will tell you B times A. Okay. So for us, the important thing right now is that these two are different. So the way to really express that is A times B. The resulting object is a matrix. It is not equal to B times A. That's the important thing here. Now, for this special example, it happens that A times B is -1 times B times A. In quantum mechanics, you speak of things anti-commuting, okay? That's not necessary for our discussion today. We just want to focus on the facts here. And right now we're observing that these matrices do not commute. Okay, so let's investigate what's going on in Appendix A2. Okay, if you read the fine print, which I encourage you to do, Appendix A2 actually requires them to be positive definite. Let's record that here. The basic premise here, one of the assumptions is that these things are positive definite. And we can easily remedy this problem. Okay, we will simply add, so we can achieve positive definiteness for these matrices by adding twice the identity matrix. Remember, this is the number 2. That's just ordinary 2, 1 plus 1. What is this thing here? This is notation we have used before. The numeral 1 with the double-headed arrow means you have the identity matrix. The double-headed arrow means it's a rank 2 tensor. It has 2 free indices. And it's a square matrix. Okay. So from the context, it's understood that we're working with 2 by 2 matrices. So this is the 2 by 2 identity matrix. And this leads us to define 2 other matrices. Okay, so we're looking at a 3, 0, 0, 1 and 2, 1, 1, 2. Okay, so the point is, having added a multiple of the identity matrix, there's no need to repeat this calculation here. We can safely assume that C and D do not commute. All right, so we've put together a list of attributes here. The matrices C and D do not commute. Furthermore, they're positive definite. What does that mean? It means if you sandwich a vector around these matrices, okay, so choose an arbitrary 2-component vector, you put the transpose here, put matrix C here. Again, this is the structure of a quadratic form. Right, we talked about the quadratic forms in our big comparison. Well, you can write this out. It's understood that this q vector is a two-component vector. The upper component is q1, the lower component is q2. So you write this out, and you see what you get is 3q1 squared. This is greater than 0 if the q vector is not the 0 vector. Okay, so far so good. And you can also show that this d is also, so it's a similar analysis for d. You can write it as a sum of squares. It's an amusing exercise to convince yourself. How can you prove that this matrix D is positive definite? Well, again, you would sandwich a vector around the matrix like so. Okay, so you take this matrix on the right, you put a column vector q1, q2. On the left, you put a row vector q1, q2. You grind it out, and you get a bunch of terms. Then, with a little divine insight, you realize you can rewrite those terms. Okay. Notice this is the sum of squares. There's no way this is going to be negative if we're talking about real numbers. So again, this is greater than 0 if the q vector is non-zero. Yep, it's positive definite. Okay, so what we have now, a couple matrices that do not commute. They're positive definite. And there's a prescription now in the appendix on how to change basis. Okay, so let's just make some general remarks on change of basis, arbitrary change of basis. Okay, so again, the topic here is change of basis. It's understood that you have some sort of original basis that you were working with. With that in mind, if you have a basis, then you can describe, using these rectangular arrays of numbers, right? You can describe these various mathematical objects such as the quadratic form, okay? What if you change the basis? Now let's use the notation that we had in chapter 10. We were talking about angular momentum. All right, so if you change the basis, we'll use a matrix F. Okay, this matrix F describes the change in basis. And let's talk about how you would do that. So you have your original angular momentum. All right, and we write it like this. We have an angular momentum vector. It's understood to be a collection of 3 numbers. Okay. If you change the basis, then relative to the new basis, you can again compute the components. Okay. And in its most streamlined form, so the very essence of this topic is that the new components of the angular momentum vector are gotten from the original 3 components via this linear operation. If we're going to allow for the most general linear operation, then we must write a matrix here. We just have one reasonable request. We request that the determinant be non-zero. That is to say, we request that this matrix have full rank. So it's a change of basis, not a collapse down onto a lower dimensional subspace. All right, so having said that, here's the situation. Okay, so again, you had some original basis, some laboratory choice of axes. And again, in room 72, we have this wonderful, it's very impressive, this Cartesian coordinate system made out of aluminum. Absolutely exquisite, work of engineering. And the point is, you have a very clear picture of a laboratory coordinate system. You have a choice of an x-axis, a y-axis, and a z-axis. And you have your angular momentum vector If you have a choice of axes, then you have the three components, Lx, Ly, Lz, okay? So you have those three numbers that describe the vector. If somebody else is using a different coordinate system, then we can compute the three numbers that they would prefer to use using this general prescription. Again, each of the new numbers is a linear combination of the old ones, and thus the most general framework here is multiplication by a matrix F. Okay, the same is true for the angular velocity. Okay, and now we can work out the implications, because certainly we know something to be true. Okay, these two objects here, I'm going to use a different color now for clarity. Okay, those are two vectors. They are described in terms of the original coordinate system, and we know the following to be true. Okay, we know that there's a relationship between the angular momentum vector and the angular velocity vector. Again, it's matrix multiplication. This is an example of an operator, right? An operator, as the input information, you have a vector, the output information is once again a vector. That's an operator. It's in contrast to those quadratic forms, where the input is a vector and the output is a single number. Okay, so we would like the same to be true over here. Let's do this. Okay. So the person who is using the different axes, these are the primed axes. They have their own description of the angular momentum vector using these three numbers here, the L vector prime. And for them, that vector is the transformed inertia tensor. There it is. The inertia tensor with a prime, that's the transformed inertia tensor. Okay. So both of these must be true. Okay. Now what you can do is plug in over here, L prime, you insert this result, it's F times L. And then the omega prime, you insert this result, it's F times omega. And then you, again, have this notion of the resolution of the identity. The conclusion is that the primed, I should put the conclusion down here. Right, so you're going to plug in here, this is F. And so what we have here, the transformed inertia tensor you got to be real careful here to get these symbols right. Okay, notice we have a matrix inversion. This notion here of the matrix F to the minus first power, this is our symbol for the inverse. And so the product, if you were to multiply the F matrix times the F inverse, you would have the identity matrix. Okay, so for this discussion, remember, we're allowing this F matrix to be very general. It is not restricted to be a rotation matrix or a unitary matrix or Hermitian or anything like that. It's an arbitrary matrix. The one very reasonable request is that we'd like the determinant to be non-zero so that you have an invertible mapping. You can go from the old to the new coordinates. You can go from the new to the old coordinates. Okay, so this is the transformation law for operators. So let's emphasize here. Okay, so operators transform like this. The transformed operator is gotten from the original operator by, we have the left multiplication by F and the right multiplication by the inverse of F. Okay, let's compare that with what we have for quadratic forms. Okay, so for the quadratic forms, we're going to write things a little differently. In fact, it's customary to rewrite this equation. let's take a second to observe. What if you take this equation and you multiply both sides from the right with the F matrix? Okay, so we're going to right multiply with the F matrix. Well, then over here you've got this primed inertia tensor. And again, we're taking this equation, we're multiplying on the right with the F matrix. So I'm simply going to write the F matrix here. There's not much to be done. I'm just multiplying on the right with the F matrix. Now over here, something wonderful happens if we multiply on the right with the F matrix. And keep in mind, we have the associativity of matrix multiplication. So if you multiply on the right with the F matrix, then you're welcome to put the parentheses around this F inverse and the F matrix, and those vanish, right? Because the product of the matrix and the inverse, that's the identity matrix, and the identity matrix times anything is that thing again. So therefore, we have the Fi here. Look at that, we got the Fi. We could have arranged for Wi-Fi. Maybe in the future I'll change notation so we get an interesting Wi-Fi formula. But for the moment we've achieved this point. Now we're going to left multiply by the inverse of F. So if we left multiply by the inverse of F, notice what happens. And I'm going to rewrite this slightly. I'm going to put the I matrix over here. So there's the primed object, and here's the F matrix. Okay, so you see what happened is we took this equation, we multiplied from the left by the inverse of the F matrix, and we got I equals F inverse I prime F. And then I swapped the two left-hand side, the left and the right-hand sides, I swapped them so we have this form now. In other words, we took this equation here, we solved for I. You can solve just by multiplying with appropriate matrices. We took this equation, solved for I, and this allows us to put together a summary that is useful for direct comparison with some formulas in the book. Okay, so here's our grand summary. Okay, the K prime. I'm being very careful to get these matrices right. And here's the F. Okay, so this is our grand summary. Let's put a very amazing double box around this because this, a lot of hard work went into this box. Let's really appreciate this. Appreciate this moment and savor this moment. Okay. So here's the summary and the resolution to the kind of disturbing message we were getting from that appendix. The simultaneous diagonalization of two matrices, right? That's disturbing after all that stuff we learned in quantum mechanics that you can't really do that. Here's the resolution. For linear operators, you have this formula. Okay. If the matrix you're talking about, in this case we use I for the matrix, if you're talking about a linear operator, if you change basis, then this is the relationship between the primed and the unprimed matrix. If you're talking about a quadratic form, which is what we're doing in chapter 11, quadratic form. Okay. Then you have this form. Notice here it's the transpose. Remember we used the tilde for transpose. So this is the transpose of F. Here's the primed matrix and here's F. And here it's the inverse. Okay, so in general those are different. In general the transpose is not the same as the inverse. You know, for rotation matrices it's the same. The inverse is equal to the transpose. But quite generally for an arbitrary change of basis, we're considering very large classes of changes of bases here. In fact, we will allow a very amazing change of basis. So, for example, this K matrix can be turned into the identity matrix, right? You can not only diagonalize it, but force all the eigenvalues to be unity. Okay, all those values on the main diagonal. Okay, so let's go through some calculations. This has been a rather technical discussion here, but the point of this technical discussion is to explain why everything they told you in quantum mechanics is true. You cannot simultaneously diagonalize two operators, right? Because again, if you did, then they would commute. And in general, operators do not commute. Okay. They do tell you in quantum that if two operators commute, then yes, you can simultaneously diagonalize them. All right, so then let's now go on with chapter 11 and appreciate that we're going to have some very special kind of eigenvalue problems cast in the language of these quadratic forms. So let's see how that structure emerges. All right. So we're going to return to our problem. Remember, we had a very nice clear problem. That's what I like about this problem. You have apparatus that you could easily build. You can build this and compute the frequencies and then do the experiment. We're going to see there are fundamental modes. And when we speak of modes of the system, those are solutions to the equation of motion where every component of the system has the same frequency, right? So we're going to see there are solutions here, two distinct solutions with two different frequencies. And we're going to see how to compute those frequencies. And then you, as the experimenter, you can prepare the system with the right initial conditions, okay, so that it is in a pure mode. So if you build this, then we can compute a proper, if you like, you can do this, have an initial displacement away from equilibrium here and an initial displacement away from equilibrium here, carefully measured out, so that when you release the two cars, they oscillate with the same frequency. Okay, roughly speaking, we're going to see there's one, especially in the case of equal, if the masses are equal and the spring constants are equal, all right, then there's the so-called breathing mode where you displace both cars towards the walls, release them, and then they move towards the center simultaneously, and then they move away from the center simultaneously. And one speaks of the breathing mode. It's like breathing, inhaling, exhaling. Okay. Then there's the sloshing mode where the two cars move left and right simultaneously. Again, that's for we're talking about the special case where these Ks are all equal and the masses are equal. For clarity, you can solve that very easily. And then the sloshing mode, the two cars move left and right synchronously. And then there's no extension of the K2 spring. You might as well remove it. It's not applying any forces. And so you can see you have these two also. So let's see how we can understand these solutions. Again, we'll have very special solutions to the equations of motion where everything moves with the same frequency. All right, and let's observe that there, in some sense, there's an interesting similarity with chapter 10. Remember when we talked about the motion of a rigid body, a free rigid body, meaning there are no external torques. We know there are special cases when if you prepare the system carefully, if it's spinning about a principal axis, then the solution is very simple. You have steady rotation about a principal axis. Okay. Here we have kind of a similar remark. If you prepare the system initially, talking about defining the initial conditions for an experiment and release it, okay, then the subsequent evolution will be very special in that both, in this case, both masses will have the same frequency. There could be some phase shifts, but they have the same frequency of motion. So let's see how those solutions emerge. Okay, so we want to solve our system of equations. Okay. And remember, we wrote down these matrices. wrote them out here. In fact, let's do this. Look at that. Very nice, clear picture. We must solve this system of differential equations. And this can be done without a terrible amount of effort. This will be a case where we do like to complexify the problem. So consider solutions of the following form. And here we're going to write out the arguments. The time dependence here, we've been explicit. This x vector is a function of the time t. All right. We'd like this to be the real part of some complex vector. Okay. So we're going to investigate the possibility of solutions or complex solutions, right? And this complex solution will have the following structure. Okay. We're going to see, can we find solutions that look like this? There's some amplitude here, alpha 1. And then we have an e to I. The crucial thing is we'll have two different phase shifts, but they're going to share the same omega. This is what it means to be an eigenmode. You have the same omega. Downstairs, very similar story, alpha 2. Note the omega. It's the same omega. We do not have omega 1 here and omega 2 here. We're interested in solutions that have the same frequency. We can have a different phase shift. No problem there. Let's call this delta 2. Okay, so this monstrosity, it's a little alarming, but let's understand this is a two-component vector. The entire expression here, this thing evaluates to a single complex number, right, as a function of time. And downstairs, this is a single complex number as a function of time. So this thing up here, we would call it Z1. That's the upper component. Down here, that's Z2. Okay, so in terms of, let's do a quick nose count of variables. We have 4 real constants, right? Alpha 1, alpha 2, delta 1, delta 2. So this is our ansatz. Okay, and so we can rewrite this as follows. This is where complex variables really shine in terms of simplifying our lives. Note how delightfully simple this becomes when you write it like this. Okay, so yeah, this form here is fully equivalent. In the upper form, we had 4 real, right? That thing, alpha 1, that was real. This is real. This delta 2 is real. Okay, so we had these 4 real parameters. All right. And now here we have 2 complex. So these are both complex. Okay, and you can see what happens here. This alpha 2 is the modulus of this A2 coefficient. And because of the property of the exponential function, we have an alpha 2 times e to the minus I delta 2. So what we've done here is just exhibited the modulus in the phase. Same is true. Upstairs, we have alpha 1 and an e to the I minus I delta 1. So that's just a way of describing an arbitrary complex number, A1. Okay, so now we plug into the equation of motion. We take this form here. All right, we're going to see if we can satisfy that differential equation with a complex z. And of course, we love differentiating these exponentials. I mean, who wouldn't? All you do when you differentiate, you bring out a multiplicative factor of I omega. If you differentiate twice, no problem. We got I omega times I omega, also known as minus omega squared. Okay, so what we have here, we can write it in the following way. We have an A vector, which is obviously this A1, A2, the two complex numbers. Okay, and now it's very important to notice that e raised to any power can never be 0. So here we've got e to the I omega. This cannot be 0, so you can safely divide both sides. We're going to divide both sides by that, and poof, it's gone. Okay, so now we can rewrite this. And at this point, we reach a major milestone. This is what Taylor calls the generalized eigenvalue problem. Okay. Let's put a box here, and let's take a second to take stock in what we've achieved. We must solve this problem. Notice the time dependence is gone. It canceled out very nicely for us. This is simply a problem from linear algebra. You're given two matrices. There's a K matrix, there's an M matrix. Okay. We would like to find a vector A and this constant here, omega squared, so that this becomes 0, right? Generalized. Okay, notice we could left multiply by the inverse of the M matrix. Then it would truly resemble, right? So let's observe. Taylor prefers to go with this generalized eigenvalue equation. But notice if you left multiply by the inverse of M, okay, there's the inverse of M. We're multiplying from the left. Omega squared is the eigenvalue. And the inverse of M times M, that's the identity matrix. Okay, so you see if you left multiply by the inverse of M, you recover, this is a standard eigenvalue problem. All right. So we really shouldn't be too dramatic here about this generalized eigenvalue equation. If you left multiply by the inverse of M, you recover a standard eigenvalue. So this is a standard. Okay. Now notice the inverse of M times K. When you multiply that out, you get a square matrix. In general, that square matrix will not be symmetrical. Okay, so that's one little fly in the ointment, so to speak. We do like it when we have symmetric matrices. We'll see both K and M. In general, these are symmetric matrices. So oftentimes, Taylor prefers to work with this generalized eigenvalue equation. So we're going to have this statement now. You know from linear algebra, if this matrix times a vector is 0, and you would like to have a non-trivial solution, obviously you could do this with a 0 for the A vector, but that is just saying everything is motionless. We're not interested in that. We'd like to have the actual system in motion. So if you want a solution with a non-zero A vector, then it must be true that this quantity in parentheses, which is a square matrix, it must have a vanishing determinant. Okay, so this is one of the centerpieces of the chapter. Okay, so oftentimes we will go with this notion of the generalized eigenvalue equation. You must first solve this. This is an algebra problem, right? Notice omega squared, you only have even powers of omega when you evaluate this determinant. So you could introduce another variable for omega squared and then solve this problem. Again, this is now purely an algebra problem. When you evaluate the determinant, you get just an expression, some polynomial in omega squared. All right, so that's the problem to be solved. Okay, so we can do this. Let's take a minute to do this for, right, we like to have some nice concrete examples. Again, this wonderful example with the railroad cars. Let's go through the motions and see how this works within this framework, the new framework of the generalized eigenvalue equation. Okay, it's useful, right, you know, things can get a little messy sometimes. So we'll look at a special case. We can enjoy all of the wonderful new things here in this world of the generalized eigenvalue equation. Now, by looking at a special case, we'll have the two masses be equal. So that means M1 is equal to M2. Okay. And for really clean notation, let's just simply call it, we have one mass parameter. Let's just call it M, little m. A similar idea here with the springs. We're going to assume all three springs have the same spring constant. Okay, so if we do that, it helps to simplify the discussion, and we can discover all the amazing things that we'll see. The existence of these fundamental modes, and when we say modes, these are solutions to the equation of motion. So these are actual equations you can write out that describe the time evolution of the system. They tell you about the locations of the particles as a function of time. And we'll see the breathing mode where the particles come together and move away synchronously. And then the sloshing mode, like the windshield wipers on a car, so to speak, and this typical left-right motion where they're synchronized, moving to the left simultaneously, then moving to the right simultaneously. Okay, so let's see what happens here. We have to write out this determinant. So this is now our fundamental equation here, solving these generalized eigenvalue problems. Here we go with the determinant. Okay. So we do have an off-diagonal element, and we get the remarkable structure that emerges here. We get a 2k minus m omega squared minus k squared equals 0. So you can see what happened here. We computed the determinant of this matrix, right? Again, we copied it here. And we observed that this matrix did have off-diagonal elements. There are no off-diagonal elements here. The mass matrix does not have the off-diagonal elements. However, the K matrix does have the off-diagonal elements. And we did write that out earlier today. Notice a minus K2 and a minus K2. We talked about that earlier today. So when you compute the determinant, For a 2 by 2 matrix, of course, we have a wonderful formula. The determinant, you multiply the elements on the main diagonal, that gives you this thing here. And then you subtract the product of the off diagonal. They both had a minus sign, but they canceled. So you get this minus k squared. This is great news because we recognize a fundamental structure, the difference of perfect squares. Notice this is squared, this is squared. You subtract, so we can factor this thing immediately. Ordinarily, we would have to solve a quadratic equation, but because we can factor this by inspection. Okay, so what we're seeing here is k minus m omega squared and a 3k minus m omega squared. Okay, so this is a wonderful state of affairs. We've taken this polynomial, right? We know in general, this prescription gives you a polynomial equation you must solve, the vanishing of a polynomial. And of course, this is accomplished by factoring the polynomial. It's a polynomial in the quantity omega squared, and that's the structure that we see here. So the fact that this is 0 means we can read off the two solutions. If this first quantity in parentheses vanishes, we have a solution, okay? So there's one solution, and when I write the solutions, I'll use the notation in the book, but there's a huge red flag. Let's be very clear that there's a terrible danger of confusion. So let's write this out like so. We have, from the vanishing of this first term, we have the so-called omega 1. It's defined to be the square root of k over m, okay? And from the vanishing of this one, we have the other solution. Okay, so these are the two solutions we've chosen. Oops, I should put the triple equals, meaning this is our definition of omega 2. But the really important thing here is the following. We do have the numeral 1 as a subscript here, and we have the numeral 2 as a subscript here, right? But this is not to say that omega 1 is associated with particle number 1 and omega 2 is associated with particle 2. These are normal modes, and so this is now the mode number. Okay, so you see the danger of confusion. Because we had labeled the masses M1 and M2, there's some danger of confusion that this omega 1 is associated with mass number 1. Not true. And that this omega 2 is associated with mass number 2. Again, that's not true. So it might have been better to call this omega sub, A and B. We'll have two modes. Let's call them A and B. We do have verbal description, right? The breathing mode, that's the higher frequency one. And the sloshing mode, that's the lower, this is the lower frequency, right? Obviously, this is about 70% higher in frequency. Root 3, right? 1.73, et cetera. Yeah, so it's really important to appreciate that when we speak of modes, okay, if the system is in this eigenmode, then both particles move with this frequency, right? This is in radians per second. Obviously, apart from a factor of 2 pi, you have cycles per second. So it's telling you how quickly they move back and forth. We'll have a separate discussion about the amplitude of the motion and the phase. Okay, and when the system is in this mode with this frequency, again, both particles are moving around with this frequency. This is the breathing mode. They're 180 degrees out of phase, so they move towards each other and then they move away from each other. Okay, and the way to see that is once you have the frequencies, the question is, how are you going to figure out this vector? We must figure out the corresponding eigenvector. Okay. And it's the usual story. You take your solution for the frequency, you plug it in here, and this equation then is the equation that you must solve. There must be some non-zero vector, which makes this true. It's a so-called null vector of this matrix, which is in the parentheses here. This entire thing in the parentheses evaluates to be a matrix. Okay, so we'll do this here. We reinsert. Okay, now it would be extraordinarily bad if we use the same notation for the vectors, right? We've already called the modes 1 and 2. By extension, you would say there's a vector A1 and there's a vector A2. That would be terrible because here, these are particle indices, right? This is particle number 1. Let's put that here for clarity. This is for particle number 1. Okay, and this is for particle 2. Right. So at this point in the discussion, we have an A1, we have an A2, and this is the amplitude, the complex amplitude for particle number 1. This is the complex amplitude for particle number 2, right? So you see the danger with this notation. We have an omega 1, we have an omega 2. It's natural to call the vectors that go along with the omegas A1 and A2, but that would cause, an international incident. So we want to have great clarity in the communication. Okay, so the modes, right? Let's look at omega 1. Okay, we've determined these eigenfrequencies. Right? We know the two possible eigenfrequencies. Let's begin with this one here. Let's study the complete solution for this frequency. What does the system look like if you have this frequency omega 1? What are the two particles doing? Okay, so let's put it like this. We're going to look at again, we plug into the equation. I'm going to have to skip some of the algebra here. We conclude that the lowercase a1 and the lowercase a2, right, the conclusion is when you plug in, you see that a1 is equal to a2. And again, these are the particle indices. All right, and again, that 1, I really want to emphasize, that 1 is the mode index. So we're looking at mode number 1. If you're looking at mode number 1, you have these two particles. This is the complex amplitude of particle number 1. This is the complex amplitude of particle number 2. And for this case, we, by plugging in, you see that the amplitude of particle number 1 must equal the amplitude of particle number 2. And of course, these amplitudes are complex. All right, so let's talk about what you actually observe. Okay, so the real positions, right? X1 as a function of time, X2 as a function of time, they are the real part of the complex. Okay, and we'll call this some amplitude A with a face. So the upshot is the following structure, right? We're going to have the same amplitude. So this is a real amplitude, we'll call it capital A. And we have a cosine omega 1 t minus some arbitrary phase shift. Okay, so this is the conclusion, and now again, you have the so-called sloshing mode. This means the particles are fully synchronized. In fact, x1 of t is equal to, right? Let's write this out clearly. Note, x1 as a function of time is equal to x2 as a function of time. So it's reminiscent of like the windshield wipers on a car. On some cars, they kind of both move left and right together. Of course, here we're talking about railroad cars on an axis, so to speak, a one-dimensional space, horizontal axis. And so for this one, we have the two cars moving left and right together. And it's useful to have a verbal term to go with this. Let's call this the sloshing mode. All right, because it's like when you carry a tray with water, there's a certain unpleasant instability. The water all moves to the right, and then you tilt it, and all the water moves to the left. So it's reminiscent. That's the word sloshing here. It's useful to describe this mode. You have these two particles that move left and right synchronously. It's like someone struggling with a horizontal tray of water. Okay, the other one is going to be the so-called breathing mode. So look at omega 2. And remember, this is the higher frequency mode. And let's also observe for this sloshing mode, remember the two particles are equal. Notice the distance between the particles is constant, right? So this is a remark to help with our intuitive understanding. So note, the distance between the particles is constant. Okay, so the distance between these two particles is a constant. So therefore, that spring in the middle plays no role. If there's a constant distance, then the force that's there, if any, will simply be a constant. The frequency, you can tell, is fully determined by the mass attached to the wall that's closest to it. So it's no surprise that the frequency here for this mode, remember the frequency was root k over m. This is exactly what we expect if you have this mass and this spring constant. Okay, now for the breathing mode, we do get a higher frequency. Remember, this is about 73% higher frequency. This omega 2 is a higher frequency, and this is the so-called breathing mode. Okay. These are terms sometimes you'll hear if you go to a conference and they're talking about some molecular system. There may be a breathing mode where the entire thing kind of expands and contracts. Often the mechanical systems have this kind of mode. And people speak of a breathing mode. It's like a bullfrog breathing. Okay, so in this case, we have the A1. If you plug in, you rapidly conclude that A1 is equal to minus A2. Okay, and so the general solution, similar to what we had here, our x as a function of time is equal to, again, there's some amplitude parameter, capital A. We've got an A and a minus A like so. Cosine. The crucial thing, they share the same frequency. In this case, it's omega 2. And in general, we'll allow for some phase shift. You can absorb this phase shift into your origin of the time axis. It's not really a fundamentally crucial thing. But if you want to start constructing superpositions, right? The most general solution for the system is a superposition of these modes, right? We have the overall linearity. Then typically you do need to keep this phase shift, right? There can be a relative phase between the two modes. Okay, so this is the breathing modes. Two masses move away from each other, then they move towards each other. Let's take a second to write out the general solution just to appreciate what it looks like. Right. Remember, ever since the early days of the course, when we were studying chapter 5, we were interested in the general solution to the problem. And we are going to count the number of parameters available to us and convince ourselves that we can satisfy the initial conditions. So here's our general solution. Okay, so there's some amplitude A1. We can factor that out. That's the amplitude for the mode number 1. Okay, up here, we could have done the same thing, right? We could factor out a capital A, and this would have been the 1, 1. Okay, we got the cosine. Okay, A2. This is the amplitude for mode number 2. Okay, so that's our general solution. Notice there are 4 constants available to us. We have this constant, that's a real constant. We have this phase shift. And we want to emphasize these parameters are logically distinct from the eigenfrequencies. Let me finish drawing these red arrows and then we'll really emphasize it. So I'm drawing these red arrows. Okay, I've drawn 4 red arrows to indicate there are these 4 parameters. And that's what you want to satisfy the initial condition. Remember, we have 2 particles. We know the classical state is determined by the position and velocity. And we're talking about 1-dimensional velocity, 1-dimensional position. So there are 4 numbers in general. If you prepare this system with an arbitrary, let's see, something funny just happened to my Zoom. Okay. If you prepare this system with an arbitrary initial state, you'll have some arbitrary initial position and velocity for particle number 1. And I should not point at the A1. That's encapsulated in all these parameters. Okay, so we have these 4 parameters, like so. And these enable you to satisfy the initial conditions. Okay, and that's logically distinct from this omega 1 and omega 2. The omega 1 and omega 2, those are attributes of the system itself, regardless of the choices you make for any given experiment. Once you build the apparatus, then at that point, when you finish the construction, you've determined these frequencies. Any experiment you then choose to do with the apparatus will use those 2 frequencies, and then you have the 4 parameters that let you satisfy the initial conditions for the experiment. Okay, so we'll make some closing remarks here on chapter 11, normal coordinates. And I'll tell you right now, for the final exam, we will not be including this material on the normal coordinates. Okay, but it's too early to start worrying about the final exam. Okay. But the point is, in general, when you study these arbitrary systems near an equilibrium, you can, very much in the spirit of classical mechanics, we know that we can define arbitrary coordinates, right? We have this notion of generalized coordinates. Okay. And the notation we like to use for the generalized coordinates, we like to talk about a Q1 up to Qn, where that little n is the number of degrees of freedom. Okay. So for these problems, when we talk about normal coordinates, okay, we're going to use the symbol lowercase c. All right, here we go. Lowercase c1, that's a lowercase c. It's like the English x. Lowercase c, here's a lowercase c with a subscript n. So this is a special choice Okay, what we do want to emphasize here is you have the ability in classical mechanics to choose generalized coordinates, right? You have great freedom to choose generalized coordinates, and often it can be very profitable. So these normal coordinates are a special choice of generalized coordinates. All right. Okay, so just in order to assimilate these new concepts into our worldview, we're very familiar with the notion of generalized coordinates. And what we'll talk about a little more next time is for these problems with the oscillations, we can talk about normal coordinates, in which case the problem simplifies dramatically. And it's going to be equivalent to this notion of diagonalizing matrices. All right, so that's appropriate level of detail for today's lecture. I'm going to stop the recording and then I'll stay here for questions.